right, welcome to video 3. We are going to go back and visit the bomb calorimeter, and we are going to be calculating heat of combustion when we know the heat capacity of a bomb calorimeter. So one thing to know about bomb calorimeters, or any calorimeters for that matter, they're part of the surroundings that are absorbing heat from the system that's being reacted. So good calorimeters have a very, very low heat capacity. However, bomb calorimeters made of metal, they're going to absorb more heat than, let's say, a coffee cup calorimeter that's going to absorb less heat because it's made of an insulated material. So when we're doing bomb calorimeter problems, we have to take into consideration how much heat is being absorbed by the outside shell of the calorimeter itself. And to do that, we have to make this calculation called heat capacity. And the heat capacity is defined for the amount of heat needed to raise the temperature of an object by 1 degree Celsius or 1 Kelvin. And there's your formula there. We denote heat capacity with capital C. Here's your heat value. Heat divided by change in temperature is going to give you the heat capacity of any substance, or any object for that matter. So I'm going to let you pause for a second and write down this formula. And then we're going to watch a quick video on how a bomb calorimeter works. So when I play this video, know that if the sound is very wonky for you, you can pause the video there, go back to your Schoology page, and open the link instead if the video is not working appropriately. Here we go. Oh, by the way, this is from the University of Oklahoma.
This short video will demonstrate how to properly prepare a bomb calorimeter for analysis. There are two main parts to a calorimeter, the bomb and the calorimeter itself. In preparing a sample for analysis via bomb calorimetry, a press is used to generate a solid pellet from a powder. Prepare the pellet press by placing the solid end of one cylinder face up in the bottom of the press. Then load approximately 1 gram of the sample into the press. With the solid face of the second cylinder facing the sample, depress the handle while applying pressure to the back of the press to avoid the press falling forward and ruining your sample and causing potential harm. A piece of iron wire of known mass is fused to the sample, and the mass of the new aggregate is taken to obtain the mass of the sample by difference. The fused sample and wire are loaded into the calorimeter by threading the wires through the small holes on the lead inside the bomb. Once the sample is loaded into the bomb, the large stainless steel ring is fastened to the base until the ring is hand tight. Do not continue to try and turn the ring, as it makes it difficult to open the bomb for further use. At this point, the bomb is ready to be pressurized. An oxygen manifold is attached to the appropriate tab on the bomb and filled to approximately 20 atmospheres with oxygen by slowly turning the front knob of the oxygen tank regulator. When the bomb is pressurized, turn off the flow of the oxygen, release the tab on the oxygen tank regulator, then remove the manifold from the bomb. After the bomb has been purged twice and pressurized with 25 atmospheres of oxygen, load the bomb into the calorimeter and add 2 liters of water from a volumetric flask. There should not be any bubbles that leak steadily from the calorimeter. If this is the case, you will need to consult your TA for further instructions. The electrode leads are attached to the bomb and the cap is placed on the calorimeter. The rubber belt is threaded on the stirring mechanism and the motor is turned on. At this point, the bomb calorimeter is fully prepared for analysis.
Okay, so a couple things there. First and foremost, they are using benzoic acid as their chemical to standardize the heat capacity of the calorimeter. Benzoic acid is a standard in calorimetry chemistry. Usually calorimeters are standardized first by using that benzoic acid so that they know the heat capacity of whatever calorimeter they use. All calorimetry scientists will use that benzoic acid as a control so that the results are standard throughout whoever is going to do a test on a particular food, let's say. Second, I just want to point out, you might enjoy how many times they say bomb in that video, just to let you know. So let's see how this works in terms of a calculation. Okay, so this particular example problem, we're going to pretend to standardize our bomb calorimeter first by loading it with a certain amount of the benzoic acid. Then we are going to get the heat capacity of the calorimeter, and then we're going to use that heat capacity of the calorimeter, which includes the water and the shell of the calorimeter itself, in order to figure out the enthalpy of combustion of what we're studying, and we're studying, in this case, glucose. So there's my little structure for benzoic acid. It's on a benzene ring, and here is the what's called your your ester group. Excuse my little break in thinking there. So first and foremost, I want to figure out how much heat was released from our sample of benzoic acid. So I'm going to get my pen working appropriately. And I'm going to say I've got 0.579. Erase that a little bit. Grams of my sulfuric acid, or my benzoic acid. And a literature value for benzoic acid is that 26.38 kilojoules of heat is released with every gram. And that's a standard that all calorimetry chemists will use. So I'm going to cancel out the grams. So for this calorimeter, negative 15.3 kilojoules of heat were released. And this is my heat of my benzoic acid. And because that's the heat released by my benzoic acid, that's going to be the heat gained by the calorimeter. So now it's time for us to get the heat of that calorimeter. And the heat of the calorimeter we'll denote with the heat capacity of the calorimeter, and we'll call this C bomb because it's a bomb calorimeter. And 15.3 kilojoules of heat were absorbed for every 2.08 degrees that the temperature went up. And this is going to be degrees Celsius. So the heat capacity of the calorimeter, how much heat it can absorb, is positive. Rewrite kilojoules per degree Celsius is going to be 7.34 with 3 sig figs kilojoules per degree Celsius. So that's how much heat that bomb calorimeter can absorb. So now we can figure out now what's happening with the glucose. So if this is the heat that can be absorbed by the bomb calorimeter, then we can figure out how much heat was released by the glucose by using this formula here. The heat lost by the glucose is going to be the amount of heat that can be absorbed by the calorimeter. And notice I flipped that sign again because now this is the heat released by the glucose. And it can release negative 7.34 kilojoules for every degree Celsius. And the glucose had a change in temperature of 3.64 degrees Celsius. So my degrees Celsius cancels out. And so the heat released by my glucose was negative 26.7 kilojoules. So now I know how much, when I burnt my glucose sample, how much heat was released from the glucose and also absorbed by the calorimeter and the water inside the calorimeter, so on and so forth. So now it's time to get my enthalpy change. So for my enthalpy change, I know that my heat of my glucose negative 26.7 kilojoules was released for, and my mass of my glucose again was 1.732 grams. So negative 26.7 kilojoules was released for this many grams. Now it's ready to figure out how many kilojoules per mole. I gave you the molar mass of glucose at the top. I'll scroll back up, show you that I did that. There it is right there. The molar mass of glucose is 180 grams for every 1 mole. So now my enthalpy of combustion, which is a molar quantity, if I burn 1 mole of glucose, which is a lot more than 1.732 grams, if I burn 1 mole of glucose, I will release negative 2,780 kilojoules per mole. And that will be my change in enthalpy of combustion. So to go back through our steps, what we did, we first figured out how much heat was released by our standard sample of benzoic acid. We know that that's how much heat would be gained by the calorimeter. We then found the heat capacity of this particular calorimeter by taking the heat divided by the change in temperature. And so the heat capacity of the calorimeter was 7.34 kilojoules per degree Celsius. That's how much heat it could absorb. So to figure out how much heat was released by the glucose, I took the negative value of this because the glucose is combusting and therefore giving off energy. It could release negative 7.34 kilojoules for every degree Celsius. The glucose sample went up by 3.64 degrees Celsius. So the glucose sample released negative 26.7 kilojoules. And then I changed this to kilojoules per mole by dividing by the mass of the sample and multiplying by the molar mass. So again, a lot there. You'll have some practice attached to this. And this is the end of video 3 for calorimetry chemistry.